the state correspondence. And so we talked a lot about various perspectives on that, including a path integral. And again, the simplest one is to go between operators and states. It's as simple as a conformal map between a cylinder. Right? So we have a imaginary omega, which is a time. So we prepare state A here. And then what we do, we try to figure out exactly what we state prepared. Right? So this is infinite past. Right? And so the way we figure out exactly what state we have is by acting on this state with some conserved charge Q. And so what we know that to go from the states to the operators, all we have to do is to go to the Z plane. And so once we do that, so the infinite past is being mapped to the origin, and that's why the state that we prepared way at minus infinite time becomes a local operator, A00 bar. Okay, and so this contour that allows us to measure what kind of the charge that we add on the operator becomes just a contour on that plane. Okay, and so this is so now the correspondence here, we have a charge Q acting on the operator. So on this side, it simply becomes that I have a charge Q acting on the local operator A. And so this is a contour integral dz over 2 pi I. And so here I have a conserved current J of Z, and I have an OPE of that conserved current with my local operator. Okay, so we discussed it. So this is how we started. I think we gave more discussion to these based on the path integral formulas. But what I want to go back to this idea because notice here what happens. So if we act with some operators, right, on the Hilbert space, we map states to states, right? So on this side, Q, so I started with the state A. Q acted on A gives me another state, right? So here we have map, state goes to state. And so what we actually have on the right-hand side, the way you can see is that I have a local operator, and then I act with it with a local conserved current corresponding to the charge. And so I have a new local operator. And so following this correspondence, a map of states to states translates here as a map to operators. Local operators go to operators. And so let's discuss this in some more details. So one simple example, and actually very powerful one. When as our charges, we use the Virasoro generators, right? So I have so this is mapped state to state. And so that correspondence, so in this particular case becomes dz over 2 pi I, and here I have z that n plus 1 z of 0, 0. Okay, so this z of m, t of z, that's one of the infinitely many conserved currents in the form of CFP. And so what I can do, so just to make this very precise, here I have a state mapped to a state, right? And so here I can write it down as an operator. So Lm. The dot means action, so it acts on A of 0, 0. Okay. Yeah, this is yes.
Can we view the state A as the state obtained by applying the operator A at 0.00 on vacuum?
Yes, that's exactly, okay, so this is what we discussed in a way, but that's exactly what it is, right? So the idea here is that this is, you have to think of this as being an initial state. And so when you are in this omega frame, right, meaning that you are an infinite cylinder, time runs from minus infinity to plus infinity along the side of the system. So here, the theory is conformal, so it's invariant after we make holomorphic transformation planes. And so the point is that if we make a map that goes to e to the minus omega, and we ask the question, if we prepare something at minus infinity, what that will be on the z plane. And so what we will find out, whatever is happening here, get mapped into something at the origin. So it's natural to think of this as a sub-local operator. And we extended this idea, in discussing a lot of details and showed using passive integral how to make it precise. In particular, how you tell me what local operator you have there, and I can tell you exactly what the Schrodinger wave function is. Okay.
So the equal sign is not exactly an equal sign. It means
right. So I don't know how you write it. So it's in the sense of equivalence, or if you wish, isomorphism. So there is an isomorphism in the Hilbert space, right? When we map states to states, there is an isomorphism between local operators. Okay, so very good. And so actually, just if you use this, so this is a definition, right? So this is a definition. This is what I mean by the idea that there is an action of a charge on a local operator, so I must get some other local operator. And so, from this definition, it follows A of 0, bar. So this is equal sum A equals minus infinity to plus infinity. That is minus m minus 2 ln dot A plus 0 bar. Actually, I'm summing over k. And I deliberately choose the index to k here. And you can see that that's indeed the case, because all I have to do, I just have to substitute. You can see that that's indeed the case, right? So the way to see this is if you substitute, if you take this expansion and substitute it here, then you end up computing the integral with respect to z. And so that's going to be over 2 pi I, z to the m plus 1, z to the minus k minus 2. And so this integral just delta m comma k times 1, right? And so this guy does not depend on that, and so you indeed recover what you expect. So here we have an explicit relation, right? So you ask me, so you are telling me that there will be a map. You give me a local operator, and you act with it on a conserved charge. It maps local operator to a local operator. And so here we explicitly showed this, right? So and moreover, we showed that whatever these coefficients are, they are the coefficients of the operator product expansion of the stress energy tensor with our operator. And so let's go ahead and continue discussing this, right? So before, I'm just going to write down 2 lines emphasizing this last point. So recall what we talked before, that if I have an OPE of stress energy tensor with any operator A, right? So there will be a singular terms in this OPE. So I give an OPE, and I am looking only at the singular terms in the operator product expansion. And so what we showed before using Mordai dynamics is that actually these coefficients are the ones that determine conformal transformation of our operator, right? So delta A of z bar actually equals minus epsilon sum n equals 0 to infinity 1 over n factorial del n bar, Z bar, and then plus del bar, the Z bar, the n of Z bar. Okay, and so that's a transformation when we make Z goes to Z plus epsilon V of Z and Z bar goes to Z bar plus epsilon Z bar. Okay, so the singular parts, so this is what we showed before, the singular parts in the OPs with the stress energy tensor is fixed if we know how does our operator transform under conformal transformations. And so in particular, if we have a tensor operator, right, so if A is an operator of a given weight, right, so we know that this operator has particular holomorphic and anti-holomorphic weights. So then we know for sure that that this OPE, so it might have lots of singular terms, but it's important that 1 over z squared and 1 over z terms are being fixed. So I have h over z squared a of 0, right, plus 1 over z delta. Okay, and then there are non-singular terms. So if you look here, again, this is what I'm just reminding you, so we discussed this a lot previously. So if you compare this, right, with the first line in the OPE, so you immediately know that, and also compare it with this line, right? So this line defines if I act with Virasoro generators or my local operators, it will transform operators into operators. So the question is, what are those operators, right? And so, just comparing, so we compare this guy, right? For example, immediately with this guy. So what you see is L minus 1 acted on A, e.g. del A. Okay. And then I have L0 acted on A, H times A. Okay. So we have it written very explicitly. We act with a conserved charge on the local operator. We get a different local operator. The PD provides a map between local operators. So this is in a holomorphic sector, and of course, exactly the same goes on in the anti-holomorphic sector. So what I wrote here is general, right? So if I have a tensor field, meaning that it has a appropriate transformation properties under the scaling, right? So because those weights are defined, how does my field transform when z goes to a constant scale factor times z? So those are the weights with which the operator transforms under the scaling transformation. And so in general, there can be more singular terms, but what we mentioned is that there is a special type of fields. Those are primary. Those are the primary fields, right? So operator O. And so if those guys have a conformal weight H and H tilde, then for these particular operators, so what we know that there are only two singular terms that end in the OPE, right? Plus 1 over z. And so additional singular terms are missing. So this is an important fact. Now, because the additional singular terms are missing, right? So if I have Ln acted on operator, right? So Ln with say positive n, right? N larger than 0. So you can see that what I have to do, I have to pick up 1 over z to the power n plus 2, and such things are absent in case L equals 0. So what this tells me, that this guy vanishes. Okay. Because see, if I put n equals 1, then the singularity starts. So for example, for n equals 1, so this guy would come up with 1 over z to the power minus 1 minus 2, L1 whole, right? And so this is z to the minus 3, and there is simply no term 1 over z, it's OPE. And so if you start increasing n, what you end up doing, you end up picking up a higher singularity and a higher order flow. And when we talk about the primary field, there is nothing here, which simply means that that if I add with Ln of positive n on the local operator, and that local operator is primary field, then it vanishes. And so that tells you so this is special, and so what we're going to call this primary field are highest weight operators, right? So who is called highest weight. Highest weight operator. If it is annihilated by Ln with positive n. So if Ln acts on O equals to 0 when n is positive. And so what we just showed, we showed that the primary operators are the ones that are actually highest weight field. So note something that we showed before, that if I start with any operator, right, and it has a given conformal weight, and I act on with a lowering operator, right? So L with positive n are lowering operators. Then the conformal weight decreases, right? So you see, where do they have it? Yeah, so in particular, so if I have some operator, right, and it has a given conformal weight, H, right? So if I act with Ln on this operator, so then I will get an operator. So this is another operator of state, if you wish, which will have a conformal weight H minus n. Okay. So what this means that, but eventually, if I keep acting with the lowering operators, I will get an operator which will be ultimately annihilated by further application of Ln. And so if we act with a bunch of lowering operators, bunch of Ln or positive n, we finally reach the highest weight state. meaning that it's going to be annihilated by any other application of Ln. And so what this implicitly assumes is that with the CFTs, so implicit assumption, implicitly L naught, so L naught is an operator, so it has a set of eigenvalues, right? So those are the eigenvalues, the H's, right? Are the eigenvalues of operator L naught in the CFT. So implicitly, this assumes that L naught spectrum is bounded. It's bounded from below, right? When I'm saying that take an operator for given scaling dimension and act with lowering operators, you will get eventually to an operator that's being annihilated by everything. And you know that every time you act with a lowering operator, you decrease the weight. So what this implies that I'm assuming that in my CFT, the set of all possible H's is bounded by from below. Okay? Is that clear? Now, is there anybody who can tell me why that's a reasonable thing? So we will prove in a second a stronger constraint. So in particular, we will show that H in a nice class of CFTs, H is actually positive. So it cannot get to negative. But I'm asking you, what would have happened if I have a theory in which the set of all H's would be unbounded? Somebody tell me what it's going to be. What is L? Right. So what's L naught? L naught is the operator whose spectrum we're interested in. So it gives you eigenvalue, right? Now remember, what's the energy in this omega frame? The energy in the omega frame is L naught plus L naught tilde plus central charge times something. So if you know that L naught has a spectrum which is not bounded from below, what it immediately tells you? It immediately tells you that in this frame, the energy is unbounded from below. What this tells you? This tells you that the theory that you are talking about doesn't have a ground state. Okay, and those are not a nice series. So before you start constructing your perturbative expansions, you better fix out the ground state. Okay, so that's why in all normal CFTs, the way so there is a well-defined notion of this highest weight operator. Okay, so good. So now, as I promised, that we can show that actually in some very nice class of CFTs, H must be positive. Okay, and so what is this nice class of CFTs? So this nice class of CFTs are the unitary CFTs. Unitary CFTs. So let's ask the question: what kind of constraints come from when we impose a unitarity on our CFT? Well, to have a unitary CFT, so for a unitary CFT, what is happening is that there must be a well-defined inner product, right? So there must be a positive inner product. On the Hilbert space. And so the way how, so of course, once you have an inner product, you can define a notion of the adjoint operator, right? And so the unitary CFT is defined in such a way that the adjoint to the Virasoro generator is the Virasoro generator at negative F. So this is a definition. So definition of a unitary CFT, right? So again, I want to emphasize, once you tell me the inner product, then I know what do you mean by the adjoint operator, because the inner product implies that I have alpha, and so here I have some operator A acted on beta. Then if I have an inner product that satisfies all the necessary axioms, so this is the same as the adjoint of A acting on alpha, the inner product is B. Okay? So the inner product itself tells you what the adjoint is. And so a unitary CFT is a CFT with such inner product so that it relates Virasoro generators for positive and negative M. And so now I'm going to show that if we have the unitary CFT, then the weights of primary fields can only be positive. So this is a very trivial computation. So I'm going to show you only two constraints. So the first one is HO equals to 0. So it must be positive in a unitary CFT. Now the second condition I will show you is that operator O is holomorphic, is anti-holomorphic. If and only if, I think I'll show only one direction, but we can extend it the other way. If the operator is holomorphic, well, the other way will be obvious. So if it's anti-holomorphic, then the holomorphic weight must be 0, or the anti-holomorphic weight is 0. Okay? So remember that the operator, if I talk about an operator in general, it will have holomorphic and anti-holomorphic weights. And so what you can do, you can show that in the CFT, the operator is holomorphic when the anti-holomorphic weight is 0, and the operator is anti-holomorphic when the holomorphic weight is 0. So those sounds like a trivial statement, but we'll see that they can similarly rather simply show. Good. So let's start with the first one. But of course, the weight can be also 0. Somebody can tell me the operator in the CFT that has 0 weight. Sorry? I'm asking an operator that has holomorphic and anti-holomorphic weights being 0. You're right. So the scalar in the, but let's, so that's a field, right? I'm asking.
It's also an operator.
Yeah, it's not. Yeah. Well, it depends. Let me put it. Yeah, you can always say, I'm looking for something better. Yes, you're right. H. An example is the scalar Q X. Right? No. What happens with what the operator? I'm talking about CFTs in general. Okay, so I'm talking about the operators that every CFT has. Identity, exactly. And identity, by definition, means that it is identity. It doesn't transform under conformal transformations, which in particular implies that it has holomorphic and anti-holomorphic weights being 0. So actually, you can show that. Well, okay, so I'm not going to go. I decided not to go into that. So there is something special with the identity operator, right? And that's, well, you guys can read it in Polchinski because I will never finish. But there is special, and that will distinguish identity operator from your example. Okay, so let's go ahead and show that statement. Okay, so what we can do, we can act with 2I0, right? on the state. Right? So there are two ways I can evaluate it. So I can evaluate it in an indirect manner by saying that, look, this O is an eigenstate of L naught. So the answer is going to be 2HO, right? I'm OO, right? And then there is another way how I can evaluate it. So I can use Virasoro algebra to write this down as a commutator of L minus L plus, L minus 1, L plus 1. So in order to do this equality sign, I have to use just a Virasoro algebra. And so this guy,
Alex?
Yep.
O as well.
It's all here. Maybe I should use A. And there will be no confusion. Yeah. I use, well, Chinsky also uses O2 for primary fields, A in general. Okay, so we're going to assume that this A is a highest weight state. Highest weight state. Okay, and which means that it's going to be annihilated by every L plus. So this guy gives me A, and then I have L minus L plus. But the problem is that I have to be careful with the signs in the Virasoro algebra. It's actually L plus or minus. So I have L plus, L minus active in A minus A, L minus L plus active A. Right? So the first step is, so here we're looking at the highest weight state. So this term must vanish because by definition the highest weight state is the one that's being articulated by L's with all positive indices. Right? And so then we are left only with this term, but that term is simply L minus A in a unitary CFT, absolute value squared. Okay, so what we know that for a well-defined inner product, that thing must be positive. So this guy up here is positive as well. So we conclude that L0 eigenvalue of the highest weight state in unitary CFT cannot be made. Good. So, second condition. So let's suppose that I have an operator for which the holomorphic weight equals to 0. Okay. So what I'm going to show that in unitary CFT this implies, so in unitary CFT, so this implies that A is anti-holomorphic. Okay, and so you can trivially extend to the other case. So how do we do that? Well, very simple. I'm just going to use exactly the same inequalities that I have there. So so we have 2HA, and then I have an inner product of AA, right? And so it must be equal to L minus 1. I write it in the state language. So L minus 1 dot a local operator A, absolute value squared. Okay, so if we have this condition that the holomorphic weight vanishes, so which means that the left-hand side equals to 0, so the right-hand side equals to 0. And one of the conditions of the well-defined linear product that L minus 1, so this tells me that L minus 1 acting at my operator A must be equal to 0. But we can go a couple pages back and we can ask, well, so this is a map. L minus 1 maps local operators into a local operator. So what exactly L minus 1 is? And we discussed this earlier today, that the operator that it maps to is just LA. So what we are finding that if we have an operator with a vanishing holomorphic weight, then it means that if I act with a holomorphic derivative, that's the condition in the unitary received field, then del A equals to 0, which means that A can depend only on the anti-holomorphic formula.
Can I have a question?
Yeah.
The equation is valid just for the origin, right? Because the A is local at the origin.
Right. So if you wish, we are. So the way to think of it this way. So that tells me that I forgot to explain something.
You can actually expand the operator around any point.
Right. That's exactly what I'm. Thank you very much for this question because I forgot. I forgot to say something that's important. So, so the thing is that remember when we do this operator state maps, right? So the minus infinity maps to the origin, and so it is at the origin we were constructing the isomorphism between states and operators. And that's a local correspondence at a given point on the Z plane. But we can do this at any other point. And so if you wish, we have Hilbert spaces at different points, right, on the Z plane. And that's very important because something that I forgot to mention where this is, so before I go any further, so as I clear about unitary CFTs, okay, so this is just additional constraint. But something that I forgot to mention is actually the way how you should look now on the OPEs, right? Here it is. A little bit more on states and operators. Right. So remember we discussed a long time ago that if I have two operators, AI and AJ, and so we talked about the OPEs, so we talked about representing a product of two operators in an infinite set. So there is some Cij with some Z dependence, right? So there is some Z dependence that I will write later, some Z bar dependence. So we kind of write this in terms of a complete set of local operators at the origin. And so, so now once we understand the map between states and operators, we can actually have a much better understanding what is meant by the OPE. And so the idea goes as follows. So suppose, well, first, let's assume that absolute value of that is less than 1. So what we can do, so we are thinking about path integral, right? And so what I have a unit, circle, right? So there is a local operator AJ here, 0, 0 bar, and then there is additional insertion AI of that and that bar. So what I can do in my path integral, well, see, if I have a path integral, I have to integrate over the fields everywhere in the Z plane. But we know that if we integrate to a particular radius, the path integral will provide for us the Schrodinger wave function. Okay. So what this tells us that if I choose to integrate over the interior of this disk, right? So if I choose to integrate over the interior of this disk, then what I will get, up here on the boundary, I will get a Schrodinger wave function. So there will be, it will carry indices I and j corresponding to operators. And it will also carry the labels, the continuous labels, z and z bar. What this tells us, that the picture here, when I have two operators, correspond in a path integral that I prepare as state at the boundary of a unit disk. So I provided some specific Schrodinger wave function. Okay, but then so this is step one. But then the second step, you know that you can use operator state correspondence. If you tell me what the Schrodinger wave function you have at a unit circle, there is a corresponding local operator to that. So this second step, what we're going to do here, so the second step tells us that in a path integral, I can represent it as a local operator, right? So we showed that we can do this for any Schrodinger wave function. I'm going to represent it as a local operator with labels ij, z, z bar. And so now I'm going to write down the specific relation, which is exactly what that means. So this local operator ij, z, z bar. So it must be a local operator. So there is ijk. So I'm expanding it in an, if you wish, complete set of local operators at this particular point, right? Or a complete set of states at minus infinity is the omega field. So 0, 0. So the index k are expanding in terms of states which have a well-defined scaling dimension. So this z and z bar dependence is just given hk minus hi minus hj, and then there is z bar hk tilde minus hi tilde minus hj. Okay. Right. So the steps here, 1, 2, 3, are the steps that we can do using a path integral formulas. And you can see that at the end of the day, we started with two operators, a product of two operators, and we showed that that corresponds to a combination, actually infinite sum, of local operators with some coefficients. And we have a specific local representation of that in terms of z and z bar, which is fixed just by the scaling dimensions of ak, ai, and aj. Okay? Is it clear? All right, guys, if it is clear for you, who can tell me where the argument will go wrong if instead of that I will say there is one more operator? Right. Oh, Z1, Z1. What will go wrong? So this yes?
The order.
In a path integral order doesn't matter. Yeah. So what I didn't say is that in doing these steps, I'm assuming that there is no other operator insertions. And I'm asking you, if you have an operator insertion, so what's going on? Why can't do the same step? Yeah, see, that's why Polchinski doesn't say it. So, okay, so I'll leave it there. We'll try to sort it out, right? Good. So other than this, are there any more questions? No? All right, guys, so very good. We're done with the CFT, and so unfortunately I don't have my Polchinski book today with me right here, but I told you what are the homework exercises. So they are very straightforward, and those homework exercises are designed for you to get familiar with OPEs and all the stuff that we learned about CFT. So now, what we're going to do, we're going to do a path integral quantization of single strings. And so that's what we're going to discuss. We talked about conical factors. So we talked a little bit about path integral for quantum field series. Now we'll talk about path integral for strings. So the way how we define at least a path integral for two-dimensional CFT. So what we did in Kolsky space-time, we talked about classical action, right? So for each trajectory, for each classical trajectory, we evaluate e to the is classical divided by h bar, and then we just put it in the integral, and we integrate all possible trajectories with appropriate boundary conditions, and so that gives us a partition function, right? So this gives us a functional integral for a quantum field theory. So we did this in the case when phi was x, right? And we talked a lot about path integral, this two-dimensional quantum field theory. Most of the stuff we did in Minkowski signature. So, so what we want to do, right? So in this path integral, okay, so the picture that you should have has to be the following. So say at t equals 0, and so it's t equals 1. So you provide a boundary condition. So this is your initial state, this is your final state, and you choose all possible classical trajectories for phi. For each of these trajectories, you evaluate the classical action, you plug it in the exponent, and you compute the path integral. So what we would like to do, we would like to use exactly the same philosophy for a string. Right, so now we move into, so this is QFT, and now we move into string series, right? So in a string series, the way to specify initial and final states is to specify, if you wish, the configuration of the string at the, say, at the initial time and at the final time. And so let the string propagate. So a trajectory, a path in quantum field theory is a wall line, right? Well, taking the wall line formula. So here, what we have is as our string propagates, it spans a surface, and so it makes natural to sum over all possible surfaces with a given boundary conditions, right? So in the case of open strings, the boundary conditions are just segments, and in the case of the closed string, right, so it will span a tube. So this is a propagation of open string. Open string, this is closed string, and very much the philosophy in the string theory will be exactly the same as here. So you provide initial and final state, and you allow arbitrary surfaces to be spanned once you keep this boundary condition fixed. The same here. So one of the questions that you might ask, so how do we introduce interactions in the string theory, right? So and where does quantum corrections coming from interactions come into place, right? And the answer is that it's actually very difficult. It's very difficult to introduce interactions between strings in such a way that that would preserve conformal invariance, right? So what we will discover, hopefully, I don't know, probably not realistic to get today, but well, in some sense, we already mentioned it. In light-cone gauge, there is a deep connection between. Well, okay, so we'll see it here. There is a deep connection between a conformal invariance and Lorentz invariance, right? Yeah, and so if we want to have string theory producing Lorentz invariant theory, then we must require conformal invariance for the string wall shape. And the problem is that if you try to introduce interactions, how you do in quantum field theory, saying that well, one particle propagates, it emits some other particle, and the other particle absorbs it. So usually, any talks like that will break scale invariance, okay, on the wall shape, and it's very difficult. So it turns out that the only way to introduce interactions, are only by thinking about different topologies for the wall sheet. So in other words, the interactions are implicitly present if you say that you look at the path integral with a prescribed, you think of the path integral as a sum over all surfaces, right? So interactions are implicit in wall sheet topologies. Okay. And so why that is the case? Well, so here I wrote a simple example. So a propagating string. So I specify final state here. It's a string, open string, initial state here. And so as it propagates, it sweeps this rectangle. But I can look at a different wall shape, right? So I can look at the wall shape. So in a path integral, when I sum over all possible wall shapes with a given boundary conditions, there will be a wall shape of this topology. Okay. So what I did, I created a hole in the wall shape. So how do I think about this? Well, so here, what I have in the intermediate state, I have still a single string propagating. So once I make a hole in the wall shape, then in this intermediate state, I have two strings. So in fact, in my path integral, which must include wall shapes of this type as well, what is happening is that this guy is actually a quantum correction. So this guy describes a quantum correction in which a string here, open string here, splits into two strings. So those two strings propagate, and here's a recombine back. Okay. So it's a quantum process in which you have a splitting and joining of an open string. So exactly the same thing happens with a closed string, right? So I can have a closed string, and so those are what people call Katz diagram. So I have a single closed string propagating, then it splits into two closed strings. And if I look at the single string processes, then those two strings must recombine back. Okay? So you can think about different topologies, and you can come up with various possible interactions. And again, I emphasize that the interactions in the string theory are dictated by simply allowing various topologies of wall sheets, right? So you're thinking, I'm going to sum over all possible geometries. What kind of geometries has to be included if I keep boundary space? Okay. So the example here, what's happening is that I have an open string, and so it splits into two. So this process is allowed. So in this process, what we have an open string goes into open plus open. So there is also a process I cannot draw, but that's a process where you have what you are doing. You are cutting out one hole, and you are cutting out another hole, and you are attaching a tube. That's also a wall shape, right? With even boundary conditions. Yes.
So
So in string theory, we don't add any, like in quantum field theory, any intact integer. So there's only string.
There is only string, and so all the interactions, all the stuff that, you know, people talk about how does standard model X series come from. That's the power of the string. You don't put anything by hand.
So I mean, for example, if we want to calculate something like a process in QED, we just choose a Volsky topology and do that calculation, calculate the amplitude. But then how would you get the QFT as a limit of string theory? It seems that you always get a kind of single particle state. Or
Well, no, that's not true, right? So you already.
because in the inaction, you do really.
So you get a single string state. That's a correct state, right? So because notice that all the topologies that I'm discussing have a single string at the beginning and a single string at the end. So it is correct what you said that I will get a single string state, but it doesn't mean that I will get a single particle state because the string has lots of internal degrees of freedom, right? So remember in a light cone we've been quantizing string and there were states with different spin. So when people build up a low energy effective theory that leads to, say, Einstein gravity and standard model H series and standard model X series, they all happen in, this single string set. Okay? So all these more complicated topologies, they show up as quantum effects. And what I'm going to do in maybe five or so minutes after I continue discussing interactions, we actually will see that, so here, so in this picture, there will be an interaction constant, right? The split or joining. And so there is an interaction constant for open strings, and there is an interaction constant for closed strings. So there are some coupling constants. So the first thing I will convince you soon, in a couple pages, is that actually the interaction constants of open and closed strings are related. Okay? And moreover, so you would say, look, but you've been lying to us. You told us that the string theory doesn't have any constant, right? The string tension is not really an arbitrary constant. It just sets a scale, right? It's a problem. So here you are talking now about interactions of the strings, and they are characterized by some coupling constant. But actually, that's not true. So maybe next lecture we will go to the E, and I will tell you that constant has to do also with an expectation value of second field in the spectrum of string. All right, so let me continue discussing. If you study various topologies, what kind of processes can happen in strings. So what can happen is that you have closed string, and so the closed string, and this is what I was talking here. So if you have an open string and you cut up two holes connecting by a tube, then you will find out that there is a process. So not here. This will be this is going to be this. So what can happen is that the open string can go into an open string plus closed string. Okay? So this is, you can think of as kind of a radiation, right? So in the closed string sector we have graviton. So this is emission of graviton, you can say. The one process is open string goes to open plus closed, and that's the examples that I will give you. So you have a tube. Tubes are propagation of the closed string. So what you will see a propagating open string. It emits a closed string, and then it reabsorbs it back. So that's corresponding to processes like that. So another processes that can happen is that a closed string can split into an open string. So we break down. And the final type of interactions is the crossover. So if I have two strings crossing, so they can reconnect. Okay? Reconnect in this manner. Okay, so those are possible interactions. Good. So one thing you might worry, so now we're kind of in this mathematical subject of computing partition sums or path integrals over various topologies and various surfaces. So the question you might ask is, well, so we know that there are oriented and unoriented surfaces. And so what does it mean when we talk about in a path integral when we sum over oriented or unoriented surfaces? Yeah.
If open closed strings can transform each other, so why these two types of strings?
Right. So good. So that's going to be one of my. Let me start with that. Okay, I'll answer your question and then I go back to what. So what is this process? Okay, so I have a wall sheet which is an analyst. I'm going to show you. Well, first of all, to answer your question is that we can look at the theory of closed strings. So it's, we can. Yeah, and so. So as long as we are at weak coupling, that's going to be it. Okay. So, but I'm going to show you that the theory of open strings are inconsistent by itself. So whenever you have an open string, you must have a closed string as well. And the example is as follows. So look at this. So how do you synchronize this? Right. So this is. I don't kind of have the, well, I can include this initial and final state, but I don't. So this is, if you wish, a vacuum diagram, right? And what is this vacuum diagram? Well, so here you can think of that I have a creation of a pair of open strings that propagate and annihilate. Right? So this is the way how I can think about the analysis. Now the building, one of the one of the guiding principles in constructing string theory, if we want Lorentz invariance in the space-time in which the string propagate, is a scale invariance, conformal invariance on the wall sheet. So I have a specific wall sheet which is an analyst, and what I can do, I can think of this as, say, Z plane, right? And so I know that whatever is happening should not depend after I do conformal transformation. I'm going to ask the question, what will happen with the analyst if I go to the omega plane? Right? So in other words, omega, right? So that was e to the minus I omega. So now I want to see how does my analyst look like there. And so the case is that if there is no hole here, then you have an infinite cylinder, right? So this up here corresponds to, say, sigma 2 equals to 0, a 0 wall sheet part. This was an infinite wall sheet part. But once I cut out the hole, the cylinder does not extend to infinity, and it ends up at some time, minus 10. So, so if our theory has conformal invariance, I have this world sheet and I can look at it from this perspective. And so I'm asking, so if I have a world sheet of this type, how would I interpret this in path integral language? And what you see here is that what you have is a closed string, initial closed string propagating over a time, capital T. Okay. So here, this is one of the example of world sheet dualities, right? Depending how you look on the, there is a geometry, right, of the world sheet, and it's specified by a topology. And you ask, now I'm going to keep topology fixed, and I'm going to keep boundary conditions fixed. And there are several ways how you can look at, how you can interpret what's going on here. So one interpretation here is that you have a quantum correction, a loop diagram, due to open strings. So this is a loop open string diagram. But this is equivalent to a tree-level closed string. Tree-level closed string. And to go from one picture to another, you just have to set up a different coordinates on the board. Okay. So, so in reality, what will happen? Just let me say one more word, and then I listen. So what will happen is that if you compute some scattering amplitudes, right, in open strings, and so what normally happens, that corresponds to propagators, right? So there are poles in the propagators, and the poles in the propagator correspond to the physical states in your spectrum. So what you will find out is that once you start computing, loop-corrected propagators in the open string series, you will find out that there are physical poles corresponding to the on-shell propagation of the closed strings state, which is simply, you will see mathematically these pictures that I showed you. You will see exactly there is a state. Since there was a different, there is a different spectrum for open and closed strings. So you can explicitly follow up and say, look, this pole that I see here, so you can lie to yourself, say, I didn't have any closed string states. And that would be correct statement as long as you don't look at the loop corrections, right? The instant you start looking at the loop corrections, you will get additional poles. And those poles will have the same mass relation as the spectrum of states for the closed string. So the theory of, so this simply tells you that the theory of open strings in itself is inconsistent. The theory of closed strings in itself is consistent perturbatively. Okay, so this is a little bit more subtle, right? So whenever I talk about, this is something that I will mention in maybe 5 or so minutes, that the more complicated topologies you see, they come up with the higher power of, so they are like quantum loop corrections, right? And so as long as you have, and so the thinking about organization of path integral for string theory as a path integral over different topologies, what you're doing, you're kind of doing a loop expansion, right, in the interactions of strings. And as long as you add any order in this loop expansion, everything is consistent. So, so in other words, if you have a perturbative expansion, then you can just look at the closed strings, and they will be okay. But the point is that the instance you will see open strings when you start talking about deep brains. So the deep brains itself, they show up in the closed string, but once you have the deep brains, you have a sector of fluctuations of this, deep brains, and so you will reintroduce back the open string sector. But perturbatively, it's consistent. So it's the inconsistency will show up only non-perturbatively. But we're not talking about deep brains at least now, and we will never talk about deep brains in the finite coupling, right? That's when they become really dynamical. So, so then there is this distinction.
Maybe this is the question. Because these two worksheets have the same topology but different geometry.
What do you mean geometry?
Well, the other one looks like this. I mean, the
To go from one to another is change of variables in the worksheet, and the theory is invariant under this change of. That's when. So what we will require from the string theory is that our string theory is invariant under change of variables of this type.
Yeah, but different geometry. I mean, they have different metrics.
Metric is not a physical observable, right? So we kind of look at the things which are invariant, and so whatever metric you, in fact, when we compute any scattering amplitude, we integrate over all possible metrics on the worksheet. So think of this way, that so let's take gauge theory, right? So in gauge theory there are gauge transformations, right? But the physical content of the theory is given by the spectrum of some gauge invariant state, right? So I have hadrons, I have blue balls, right? And so these gauge symmetries, they are redundancies. They don't show up in the physical spectrum. So in this sense, the metric on the worksheet which you're talking about, even though actually in this particular case, the metric on the bullshit doesn't matter. It's still flat in both cases. So metric doesn't change.
But what about the extrinsic curvature? I mean, how
It's still
the
zero.
bullshit is embedded?
But I'm saying that, I'm talking in more general, even if the metric would be different, I would say that still the metric on bullshit is gauge. It's like gauge degree of freedom. Okay. So, so they will not show up in any physical, observable, right?
But what about the embedding of this bullshit in the space-time? There is a extrinsic.
Well, so there is. I think the question is that you are saying that, well, if you embed a bullshit in a space-time, so an induced metric on a bullshit, right? But that's just one metric. That's what I'm telling you. I mean, there will be we can put arbitrary metric on a bullshit. And at the end of the day, whatever we compute, we have to integrate over all possible metrics to get gauge invariant quantity. So the physical content of the string is processes like scattering amplitudes, right? So I specify a state of the string here. I specify how my string is excited. So I specify what particle they have initially, what particle they have final. And I'm computing a scattering amplitude. And so I have a propagation of the string, but how exactly this propagation occurs is hidden in the path integral. I have to integrate over all possible metrics. And the physical answer should not depend. If the physical answer depends on what metric you put, that means that your theory is not diffeomorphism invariant on the
So it only depends on the topology.
Yes, so in the string theory, the answers depend on just the topological properties of bullshit. And that's what you kind of see already. So the propagation of the string, well, I mean, the interactions of the string, they are forced on you by topologies. Which is what you kind of want to have when you talk about theories that will include gravity. All right, guys, so very good. So there is a discussion about what I wanted to talk about, oriented and unoriented bullshits, but I'm not going to do that. Okay, so I don't think that's important. I mean, it is important, but there is also important time constraints. So you can read, it's very simple. In Bulchinski book about that. And we'll go ahead and we now, after this very general words, we go and actually talk about what I call path integral. We're gonna specifically study path integral for the string. And so what I'm going to do, I'm going to do only closed string, and what I call path integral. Or closed strings. And so our goal here, so that we will not get lost in computation. So our goal here is to show from the path integral in a covariant way, we're going to show that the critical dimension of the string p equals 26. And in order to do that, we're going to use, develop some techniques from the path integral in a little bit more details, compute, get some idea how do we think about strings propagating in Kerr space-time, and finally, we will use what we know from the CFT, right? So all this will be important to understand this. Okay. So what we're going to do, again, we're going to do a weak rotation and talk about Euclidean bullshit. Okay? I'm going to talk about Euclidean path integral. Okay, so in the case of two-dimensional quantum field theory, this is a well-defined procedure, and so there is still a lot of discussion. So the reason why you want to do Euclidean path integrals instead of Minkowski ones is that in the Euclidean path integral, in the exponent you have, in the Minkowski one you have IS over H. And in the Euclidean one, you have e to the minus x. So what is happening is that here you have kind of all the trajectories contribute at order 1, right? So it's a wildly oscillating path integral, but it's more difficult to kind of choose the semi-classical trajectory, right? So here the semi-classical trajectory is 1. Which minimizes the action. And compared to the semi-classical trajectory, any other trajectory will be suppressed. So the whole idea of going to Euclidean path integral is to make this path integral convergent. Okay? And it can be done in a context of two-dimensional quantum field theory, sum over all topology, right? In the case of the string theory. You can ask the same question, what about four-dimensional quantum gravity? Or just, it will become quantum gravity whenever I stick Einstein-Hilbert term in path integral and try to integrate over all geometries. And the point is that people show that there is no analytic configuration that will produce a suppression of almost everything except a semi-classical trajectory. Okay? In other words, in quantum field theories in dimensions higher than 4, which include gravity, so these Euclidean path integrals lose their convenience, modulation, if you wish. But we're in 2 dimensions, so we are lucky. And so our path integral, okay, is going to be, we have to integrate over all possible configuration of axes, right? And we're going to integrate over all possible worldsheet metrics. And so here I have e to the minus s, the action, and so the action is the action for the scalar fields x. And then I'm going to introduce, a constant lambda, and it will couple to chi, right? So this chi is an Euler character. This is Euler character of bullshit. So you have seen all of this before. So this action, Sx, this is just a Polyakov action, 1 over 4 pi alpha prime, an integral over 2-dimensional worldsheet. And then I have d2 sigma square root of g. And then I have del A x mu, del A x mu. So this is just a Polyakov action, and the index mu. The index mu runs from 0 to minus 1. And then when we discussed what are the possible additional terms we can include in the action, so one additional term that we can include is this one. So I write correct normalization here. So d2 sigma square root of g. So we started, we asked the question if we, so this guy itself, right, so it has a worldsheet diffeomorphism and it has wild invariance, and we asked if we want to keep those symmetries, is there anything else we can add? And so what we can add is integral for each scalar over a worldsheet, but you can prove that, well, actually we showed that this piece does not contribute to the equation of motion, which means that it's just a boundary term, which means that it's a topological term. So it just tells us what the, is sensitive to the information about topologies of worldsheets. And so it turns out that if you normalize it properly, then what you have here is the Euler character of a two-dimensional surface. So I'm going to tell you exactly what this is. Some of you, of course, know that, but probably not all. And even if you don't, I'll just remind you. So again, Euler character is a topological property of a surface. And so in the case of two-dimensional surfaces, this Euler character is given by 2 minus 2g minus b. So this g is the genus of the surface. It tells you how many handles you have. So this g here is number of handles. Okay. And so b here is number of boundary components.
So you don't consider non-orientable version.
Just 1 second. Yes, so we're not talking about cross caps. So there will be a cross caps in general. And I decided not to talk about the unorientable surfaces. So it's an extension. So string theory can be extended to infinity. I mean, in
Does it
complexity.
do any good to string theory if we include those cross?
Yes, that's a different type of. Okay, so what I didn't, since you asked, I probably have to mention. So remember we talked about propagation of flow sheet, right? Okay, fine. I'm going to mention this. So remember, long time ago when we talked about light-cone quantization of the string, so we talked about, in the case of open string, there is an operator which is a parity omega, right? How does it act? So it takes x mu, but it acts both on closed string and open string, right? So in case of closed strings, what you have, you just flip the direction, right? So in the case of the open string, what you say is that x mu of tau and sigma will go, if you act with homodromy, will go to x mu of tau and pi minus sigma. Okay, and then what is happening is that so this is an operation which, if you wish, flips over the ends of the open string. And then you can ask the question, okay, so I'm going to compute the spectrum of the states, and if I talk about unoriented strings, then my excitations must better be invariant under this, right? So, for example, if I have some state phi in the string theory, then all physical states in the unoriented string corresponds to a state when the eigenvalue is +1, right? So this omega operator is a projection operator, right? So it squares to 1. That's why its eigenvalues can be 1 or +1. So, so this projection on the spectrum, remember that led to a reduction in the number of massless states. So we talked what are massless states in oriented or unoriented string. So, so this guy, how can I say this? Well, so these are the physical states of the unoriented string. But what I can do, how can I get? Suppose I have oriented string states. Oriented states. Okay, and I'm going to denote them with a subscript O, and then I have an oriented string, right? States, which I denote unoriented O. So how do I get this state from this one, right? So the way to do that is very simple. So I'm going to say, well, the spectrum, in order to obtain the spectrum here, what I have to do, I have to act on the oriented spectrum with 1 plus omega times 1/2. So if my state has an eigenvalue, I'm guaranteed to have eigenvalues either plus or minus 1. Commutes with the Helmholtz Hamiltonian, all that stuff. So, so if the state is invariant under omega, it will keep it. If the state has an eigenvalue -1, what it will happen, it will project it out. I will get the 0. So in this sense, what you see here is that once you insert this projection, what you're doing, you're just constraining the, you're going to unoriented string spectrum. So now we can do the same thing in a test integral. What does it correspond here, right? So before, what you have, so without this, you just have oriented strings, right? In oriented strings, we talk about oriented surfaces. So in particular, one of the diagrams that we discussed is this one. Okay? So this is an oriented diagram. I can specify a normal to the surface at every point, and it will be fine. So now, what does it mean? What does it mean to go to unoriented string? Okay. So I still have to have this diagram because there is one here, right? In a test integral, I have to sum over all what they have in oriented case, and then I have to allow the action of this parity operator on this worldsheet. So the question is, how does this parity operator works on the worldsheet? Well, to answer this question is easy. So I have a string here. So this is a initial and final state, right? So I'm assuming that those are embedded. But here I have a loop. So I have to integrate over all possible intermediate states. And in the unoriented string, I have to insert a projection. And inserting a projection means that I have 1 times this, right? Plus omega acted on this, right? And then I have to add 1/2. So what this means? So I have to cut the worldsheet here. I have an intermediate open string, and instead of gluing it in oriented manner, I have to twist one and glue it back. So in this case, I will get, I cannot draw it, but you can imagine it. So in this way, you get unoriented worldsheets, right? So see, there is kind of funny things that's going on. You get the smallest spectrum of physical states, but you have to sum over more different topologies. Right? And so the same thing also works in the closed string sector. And actually, in order to do that, I would have to extend the discussion and include crosscaps here as well. But that's, I mean, the logic is easy. Okay, so let me go back. To here. So what we are discussing Euclidean test integrals. There is this Euler character, and the Euler character for a two-dimensional surface is given by this. You can easily compute it for a sphere. What do I mean by that? Take a two-dimensional sphere, compute a Ricci scalar of the sphere, choose some metrics. The answer will be independent on the metric you put on the sphere. So you can put just a round sphere metric, evaluate this integral, and you will get I equals to 2. Okay, so that integral, if you evaluate it for a sphere, which is the simplest one to do, you will get 2. So why do you get 2? Because if I have a sphere, so the sphere doesn't have any boundary components, and it doesn't have any handle. So the genus of the sphere is 0, and there are no boundary components. Okay, so the Euler character is 2. And as I said, that's something you can easily compute. Now, what we can do, we can go. Let's look at more complicated topologies. Right, so in the closed string, what I can do, I can have a torus, right? So here I have, you can think of a torus, how you can think of a torus, right? I keep telling you that this is number of handles. So what you do, you start with a sphere, cut up one hole, cut up another hole, connect with a tube, deform it, and you will get a torus, okay? The reason you can do deformation because everything is specified by default. So in this case, that's why the torus has one handle compared to a sphere. The sphere didn't have any handle. So in the case of a torus, you have genus 1, and there is still no boundary components equals to 0. So an Euler character here is going to be equal to 1. So finally, if I have, I can think of this either as an analyst, right? So in the open string channel, I have an analyst. Okay, that's
Pi equals 0 for the torus, because G equals 1. 2.
yeah, you're right. Okay. There is another one. With chi equals 0. So I'm kind of asking what are the possible worldsheets that have Euler characters going from top to more and more negative. So this one is endless, right? So I don't have any handles here, but I have two boundary components. So V equals 2, G equals 0. So the Euler character is G equals to 0. And this is actually the same as a propagation, tree-level propagation of the closed string, also two boundary components. Okay, so very good. So, so notice that in writing down this particle action, I introduced this number lambda. So let's talk about the physical meaning of that. So we know what chi is, okay? And so the only question remains, is there a physical meaning to this parameter lambda that we introduced? And I kept promising you over and over that that's not going to be a free parameter, and that's true, but we'll see it later. So in order to understand, what's going on, let's look at the propagation of open strings, right? So I have just a strip, just an infinite strip, so this is the simplest topology with the given boundary conditions. The next one is when I cut out the hole. Okay. So if I cut out the hole, we understand the interpretation of this worldsheet. So this is when a string splits and then recombines, splits into two and recombines. And the Euler character here, to go from here to here, the Euler character changes by -1, right? So what this tells me that, well, the reason why it changes by -1 is because I introduced one additional boundary component. So, so then in the path integral, the worldsheets of this type, so these guys come with a factor of 1, right? Then compared to worldsheets here, the worldsheets of this type will come with additional factor e to the minus delta chi times lambda, right? So, so all I'm doing, I'm just evaluating this additional suppression factor, and it will come out because the Euler character changes. Now, the Euler character changes by -1 unit. And so you see that this additional worldsheet is going to be weighted. So there is still this x path integral, but I'm saying that there is an additional suppression for the other worldsheets, the ones with the hole, that is e to the lambda. Now, in a space-time picture, what we have here, we have that there is a coupling constant here to open for the string. We need to introduce a coupling constant, because we need to specify the process of opening, of splitting and joining the string. So there is a coupling constant G0 here, and there is a coupling constant G0 here. So this additional suppression must be proportional to G open squared. Okay. So the different topologies correspond. So from here we can kind of see that the meaning of this lambda is that the open string interaction constant must be proportional to e to the lambda over 2. Now we can do exactly the same kind of exercise with closed strings, right? So here I have a sphere, and then I go from a sphere. To a sphere with a tube, right? So this is kind of the simplest process that I can imagine that happens at the interaction level. So what I did here, I added one handle, right? So delta G, the genus increased by +1, so the Euler character changes by 2. So delta chi equals to -2. And now this process I have to interpret as emission of the closed string. So there is G closed, it's a coupling constant for the closed string, and then the string is being absorbed, and so this process is also controlled by the interaction constant G closed. So what we are finding here is that e to the 2 lambda, right, must be identified with G closed squared. So the closed string coupling must be proportional to e to the lambda. So what you can see here is that, again, you might have expect from what we already discussed, there is a very close relation between open and closed strings because it's dictated by topologies. And so what you see here that you are actually not free to separately adjust the coupling constants for closed and open strings. There is a relation between them. So I have been a little bit sketchy, but you can show this. Precisely. Okay, very good. So any questions so far? So our next step is we're going to evaluate this path integral, right? So I'm going to look only at this part now, and I'm going to omit this Euler character part that simply tells me about quantum correction. So that class integral there is very bad. Okay. So this class integral dx over dg, which is minus sx, is not a nice class integral. And the reason why is because there are tons of symmetries in the problem, right? So there is this action is diffeomorphic invariant, and there is also Wild transformation as well. And so what this tells us that in this path integral, I'm going to overcome. Ideally, in a path integral, I have to sum over all distinct physical trajectories. Okay. Now, because I have lots of symmetries, what will happen is that there will be lots of redundancy. And so, in order to get rid of these redundancies, I have to divide this integration matter by the volume of the diffeomorphism group times the volume of a Weil transformation group. Okay, all the volumes are infinite, so everything that I'm going to write on today is not well defined, but we'll make sense of this eventually, right? So, so those are the redundancies in our description, right? And so again, so what I'm writing here is a single string Titian function. And so again, for now, I'm gonna look at the closed strings only, and there will be no, we'll look at, but there will be no boundary components. So because there is this huge, huge symmetry, what we can do, we have a bullshit metric, AB of sigma, and so it is a symmetric. It is a symmetric metric, right? So it has 3 independent components. But I have a diffeomorphism, 2 arbitrary diffeomorphism transformation, 2 diffeos plus Weil transformation plus 1 wild transformation, which is equal to 3 parameters. So I can use this redundancy in order to fix the metric any way I want. Often what is done is the metric is fixed. The metric is fixed to be a flat metric on the worldsheet. So this is done often. And sometimes, so this is flat, sometimes the metric is fixed to a conformal metric. So G, A, B, hat. When I write down a hat, I mean that I'm doing a gauge fixing of the metric. I use my reparametrization invariance and wild transformation in order to put metric in a specific form. So what I can do, sometimes we can put it in a flat metric up to a scale factor. So this is going to be a conformal gauge. So this is wild factor. Good. So what I claimed that we can always do that, right? So we can always use diffeomorphism invariant and wild transformation to make a metric on the worldsheet flat, and I'm going to prove this to you now. Right, so this is a different kind of gauge fixing, right? So when we did when we did the light cone quantization, we also were faced with a problem: how do we fix a blue gauge? And we fixed gauge in a different manner. And so here, I want to fix a gauge in a way that, for example, I want to have a flat metric on the worldsheet, and I'm going to argue that I can always do that by making diffeomorphic transformations and wild transformations. Okay. So two-dimensional surfaces are very simple. So using diffeomorphic transformations, you can always show that you can put it either locally flat or locally sphere or locally hyperbolic space, right? So, so in other words, you can make a metric into the, you can always use diffeomorphism. So use diffeomorphism. To bring the metric into this conformal form, right? So that's a statement, which is something that is easy to believe. If I were to tell you that you can put a metric on the sphere into a flat metric, you will say I'm lying. If only you are allowed to do is just diffeomorphism invariant, because curvature is invariant under diffeomorphism method. So there is a difference between a plane and a sphere. And so that's actually where the wild transformation comes into play, because the wild transformation allows us actually to put any metric on the worldsheet into a plane metric. And the way to do this is so let's do wild transformation. So I start with the metric GAP, which goes GAP prime, which leads to omega GAP. And so I'm asking, how does my Ricci scalar transform? And so I will find out that G prime now prime, so the prime one, is going to be equal to square root of G. Yeah, I have a Ricci scalar minus 2. This is the formula in our favorite book on general relativity, which is low. So it tells us how does various parts transform under wild transformations. And so eventually you can see that in order to make vanishing Ricci scalar, so we want this guy to be 0. So what we have to do, we have to solve this harmonic equation. And so this harmonic equation always has a solution, at least locally, which means that I can always locally find a scale factor in such a way that after a wild transformation, I will have Ricci scalar being equal to 0. Actually, in 2 dimensions, it's special because the Riemann tensor RA BCD is proportional to Ricci tensor, and here I have AC GBD minus whatever's the appropriate other units of fractions. So once you make Ricci scalar be 0, right, then you immediately make the Riemann-Tensor 0 as well. And so by doing Weyl transformations, you actually went into a flat wall sheet, and then I can use diffeomorphism in order to make a matrix delta E. Okay, so I just argued to you that I can always do this change of variables to make a metric on the wall sheet locally flat. Okay. So somehow, I told you that in order for me to put a metric in a specific form, I need 3 constraints, right? I have 3 metric components, and I'm saying 3 conditions, right? When I said this thing, so what I did, I said that G11 equals to 1, G22 equals to 1, and G12 equals to 0. So I put 3 conditions on my metric, and I had 3 conditions to begin with, 2 reparameterizations plus 1 Weyl transformation. So this counting is wrong. And let me show you why this counting is wrong. So in other words, so fixing the metric to be flat does not completely fix gauge degrees of freedom associated with diffeomorphism and Weyl transformation. So know that the gauge, and by that I mean diffeo times Weyl is not completely fixed. Okay, and the reason for that is the following. So so suppose we fix the metric to be GAB equals delta AB. So I fix the metric to be locally flat. So there is an additional transformation that I can do in order to leave the metric in this form. And in order to see this, suppose I introduce a complex coordinate Z, which is sigma 1 plus I sigma 2, and Z bar is sigma 1 minus I sigma 2. And so what I'm going to do, I'm just going to look at a particular type of diffeomorphism, right? So that goes into Z prime, which is holomorphic function f of Z. So if I do that, so ds squared, the metric on the wall sheet, will go ds prime squared, which is going to be equal to dz prime bar, and then here I have del f, absolute value squared. Okay. So naively, so I start with the flat metric, right? So the flat metric is dz bar. I think that is a factor of 2 or 1/2, doesn't matter. And so I go into a metric which would naively look different, right? So so once I do this holomorphic change of variables, I modify a metric by del f absolute value squared. However, I can also do simultaneous Weyl transformations. And so what I can do, I can make a transformation that goes to f of z, and I'm going to make a Weyl transformation with omega. Sorry guys, there is a -2 here. I can make a Weyl transformation with omega equals log of absolute value of del f, right? And so you can see that if I combine a holomorphic reparameterization of the wall sheet with Weyl transformations, I will get back to a flat metric, right? So I sort that by going back to a flat metric. I fix all possible degrees of freedom, meaning all possible diffeomorphisms and Weyl transformations, And here what I'm showing you is that in this huge group, diffeomorphism times y, there is a particular set of transformations that leave the metric flat. Okay? So is there somebody can tell me what's going wrong with my counting? I counted 3 there, and it says there are 3. 3 minus 3 is 0, so everything should be fixed. And here we have money, no, not everything is fixed. What's wrong with my counting?
But the diffeomorphism that you do basically does the same thing as a Weyl transformation.
Right, so what does that mean?
So that you basically overcome the curve.
You're on the right track. So the thing, what's going on here is that, so here, the diffeomorphisms and y's are independent. And so this count in 3 minus 3 equals to 0 must be completely fixed, works in general, okay? And so here I'm saying that it works in almost always, except for this particular subclass of transformations. So those are very special transformations. In general, diffeomorphism transformations will not be holomorphic, and then they don't have to be accompanied by corresponding Weyl transformations. So this counting here works up to transformations of measure 0. So in some sense, that infinite set of transformations that we have discovered is still measure 0 in this full group, diffeomorphism times Weyl transformation. And Joe Polchinski in chapter 5 is treating that very much more carefully, this type of things, and there is a complete counting, so it works nicely. All right, guys, so we did very good today. And so what we're going to do now, so there is 8 minutes, so let's have a break. And after the break, we will do Fadeev-Popov, we compute Fadeev-Popov determinant corresponding to this gauge fixing. And then, if we are lucky, we will compute a conformal anomaly and get the closed CFT and discover our old friend BC system.